Hello, good afternoon, everyone. Welcome to Khalifa University Community Webinars, and welcome back to the new semester, which is spring semester. I hope all of you are safe and well. Today we are going to talk about how to develop a low-cost solution for an affordable perinatal health screening. So I'm going to show my experience, how I have made a solution for an affordable perinatal health screening. So I am an associate professor of biomedical engineering at Khalifa University. We have shown that, so look at this photo. So happy baby and healthy baby means happy mother. So having a healthy baby is the greatest success and greatest happiness of any mothers in the world. However, if you look at the statistics of stillbirth means that when the baby is born as dead. And no one knows what is the reason of death. So, and mothers even do not know, sometimes mothers do not realize that the baby is dead for a few days without realizing the baby is being dead. So if you look at the statistics, 2.6 million worldwide are stillborn. So main cause of the stillbirth is not very clear. However, it is preventable if the complications are known beforehand. So if you look at the statistics, worldwide statistics published by World Health Organization, so you can see some of the developing countries have the highest stillbirth. So this rate are actually per 1,000 birth. UAE is still in the lower range, which is around 10 per 1,000 birth. So now the anxiety and the grief the mother has experienced through a stillbirth is not possible to be expressed in language. So look at this, the photo of the mother who lost her baby before the baby was born, and how sad a mother could be, a mother without a baby. And the stress and anxiety during pregnancy are enormous for any mothers, and nobody knows like why that causes anxiety, because mother cannot understand whether the baby is doing well or not. So it is important to have a tool or device for the mothers that mothers could be using that device at home without needing to go to the hospital. So just to make sure that the baby is her baby is doing well. But currently, the researchers are actually working on how to make for example, the wearable device that could be used by the mothers at home to look at the baby's health at home. Now, if you look at the limitation of the current fetal welfare testing method, first of all, most of the methods that are available in the hospital are expensive, and most of the devices have very high false positive, or called false alarms. So that means device gives the warning that mother has problem, but mother doesn't have any problem. there are many cases of this called the cesarean C-section are actually happening due to the false alarm. And another issue is that while the high-risk pregnancy are referred to a specialist, majority of the abnormal babies are born to low-risk mothers. So the mothers who are not showing any risk are actually giving the most abnormal cases because there are not much care provided to the low-risk mothers. Now, recently the diagnostic pyramid, if you look at the left-hand side the pyramid, this was the traditional perinatal care pyramid. Like that means in the beginning, like 12 weeks, starting from 12 weeks, the screening started from 12 weeks until birth. So in the beginning, there are less hospital visit for screening, and the more visit are actually happening at the end, last trimester. However, now researchers are suggesting that because of the advancement of technology, so now there is time to think that more screening should be done in the beginning than the later, when there is nothing could be done at the later stage. So the diagnostic pyramid are being flipped. Now let's look at the traditional method to assess the fetal well-being. The most common method that you can see in the hospital is cardiotocography, CTG. Now, what is CTG? CTG actually records two things. One is the fetal heart rate and simultaneously with the uterine contraction. So the midwives look at the baseline changes of the fetal heart rate in addition to the uterine contraction. So there are diagnostic method from the CTG recording developed by International Federation of Obstetrics and Gynecologists. So there are like three patterns. One is reassuring pattern. So when the baseline heart rate is in between 110 to 160 and the variability of the heart rate is more than 5 beats per minute. So that means this is reassuring, no problem. However, if the heart rate falls below 110, so 100 to 109 or between 160 to 180, and the heart rate variability falls below 5, is non-assuring. So it is not fully abnormal, but we need to test it again. But if the heart rate falls below 100 or goes above 180 beats per minute, and the variability falls below 5 or above 25 beats per minute, I haven't mentioned here. So there's low variability is also bad. High variability, that means variability higher than 25 beats per minute, also bad. So that is abnormal pattern. So now look at the normal fetus. Like you can see the fetal heart rate, heart rate variation is very clear in conjunction with uterine contraction. So normal variability is defined as 10 to 5 to 25. So, normal fetal heart rate is 110 to 150, sometimes 160. So look at the variability, how they measure. They have this kind of the measurement box, and then you can see that for this fetus it shows the 20, 15, sometimes 22 to 18 beats per minute variability. So average variability is 20. That means this fetus is healthy. So so I just explained that the diagnostic criteria. So like I'm just showing you 3 examples here. One case is the tachycardia. That means fetal heart rate is too high. So you can see the 180 beats per minute. That means this is abnormal. So another pattern is that late deceleration. So you can see that the baby responds a bit later. So that when the contraction happens, so heart rate responds later. So heart rate drops. And then another abnormal here, you can see that the contraction happens, the heart rate decelerates, heart rate drops, but it doesn't, goes back to the baseline quickly. So it's called the prolonged deceleration. This is the abnormal signs of fetal heart rate. So another important abnormal fetal heart rate sign is the sinusoidal pattern. So we can see the uterine contraction with two cycles here, but we can see there are many cycles in heart rate, which is also abnormal. It shows that the baby is lacking oxygen. Fetal echocardiography is very popular, so we call it ultrasonography, and then baby can be seen in the ultrasonographic video, and then mother can see her baby is moving, baby's face, shape, hand, leg, and everything, and the heart, and all the internal organs as well. This is only possible in the hospitals. Of course, you need to go to hospitals, have this the facilities to have the fetal echocardiography. So another existing solution is currently available in some hospitals, not all hospitals, called the fetal electrocardiography. So most of the hospitals have the fetal electrocardiography machine that are able to detect the fetal electrocardiogram from the fetal skull. But this solution is the non-invasive fetal electrocardiogram. That means this through this device, the fetal heart electrical activity can be measured by using the abdominal sensors. Like you can see, there are abdominal sensors on the maternal abdomen, and then we can see the fetal ECG and also maternal ECG. So this device was developed by Atom Medical Corporation in Japan, but current market price is around $60,000. But this device is very useful because you can see that one of the example here, the abnormal beats are detected through the ECG. We can see the PVC, called premature ventricular contraction. Another advantage of the fetal ECG is that we can see that the shape of the ECG during uterine contraction. For example, in the upper panel shows the CTG trace, and the lower panel shows that the heart rate estimated from the fetal ECG. So you can see that in the contraction, so you can look at this contraction, uterine contraction, and you can clearly see that the ST depression can be seen. So ST depression happens when the fetus get less amount of oxygen. So we can understand more about the fetal conditions through the ECG signal rather than just looking at the heart rate recording. That is only possible in CTG. ECG device can also give more understanding of the fetal arrhythmia. For example, here you can see the premature ventricular contraction. The red box shows the premature ventricular contraction. And also from the ultrasonography, you can see the double blood flow. So the red one is the premature ventricular contraction. And we can clearly understand that the fetus have some abnormality in the conduction system. So these babies could be saved by putting pacemaker after delivery. So this is another case of the ventricular arrhythmia. You can see the PVC at 28 weeks, and the pacemaker was fitted after the birth. In the wearable monitoring device available in the market, there are two monitoring devices in the market. One is Doppler based handheld fetal monitor. It's very cheap. It's only $100. But this problem of this device is the active Doppler signals transmission. So a Doppler is kind of Doppler device sends the high frequency sound signal to the baby, and the reflected sounds gives this information about the fetal heart rate. But the high frequency sound for long term is not good for baby's health. So it can be used for short term, of course, but the problem is that this sensor needs to be adjusted, and sometimes mother may not get the fetal heartbeat correctly if she doesn't know where to put the sensor. It all, of course, requires gel, and then proper placement of babies is too difficult for mothers. So another device that is also available in the market is fetal monitor based on ECGs is Monica fetal monitor. But this device can be used only after 35 weeks gestational age, and market prices are currently over $8,000. But this electrode setup is very difficult because it needs skin abrasion to attach the electrode to get the better signal. So some mothers may not be able to attach the electrode correctly, and that causes problems. So I got some feedback from some mothers who use this device. They said that the signals are not reliable because the electrode attachment was not properly properly done. And then this electrode is also expensive. It's $50 per set currently. This is special gel electrodes, and that is only disposable electrode, so it cannot be reused. So now, if you look at the healthcare spending per capita in 2017 statistics, so if you look at the statistics like in terms of the color, so you can see that the light color are less than $50 per person, and the highest color we can see more than $5,000. So we can see the deepest color is some European countries, Australia and the US are the highest per capita healthcare spending, and the poor countries is less than $50. So there's a big discrepancies in the healthcare spending. And if you look at some of the photos, like I took this picture from the community clinic in Bangladesh, and they use in the rural clinic, they don't have any device except the stethoscope, and they only measure the fetal heart rate through this stethoscope and then give the diagnosis that whether the baby is doing well or not. And also in those settings, so sometimes they look at the baby's health by just touching on the mother's abdomen. So now the challenge is that how can we ensure that the women and newborn survive and remain healthy during pregnancy and childbirth in low resource setting? That is a big challenge for all of us. So now low cost means that the affordable range. So affordability is also varies from country to country. So universal affordability from the medical device perspective is something less than $100. And when the Satyendranath Bose, who was the father of quantum statistics and physics, and he was in a conference, and he was asked a question that how come someone from India did what so many Americans could not? So he famously replied, "We didn't have money, so we had to think." So when you don't have the money, so we always think how to find the solution. So the working principle to reduce cost is we thought about how to reduce cost. So first of all, first principle is that we need to make sure that no new capital costs are added. That means no use of telephone network, no calls, no SMS, no data transfer, no reagents. So these are the costs that can actually increase the device cost. The second thing that second principle that we can reduce the cost is that don't rely on distant expert, because if you, I know that telehealth is very getting popular, but you need to pay the providers for this telehealth consultation. So create an application that provides useful answer directly to the health worker in the clinic, so no delay, so it doesn't go through this the distant experts. So that means the interpretation should be easy enough for the healthcare worker to understand whether the baby is doing well or not. So this is the second principle. The third principle is that avoid the need for training wherever possible. So when the device is actually budgeted, so the training is also part of the cost of the device. So if you remove the need for training, so you can also save the cost of the device. So these are the three working principles that we thought about when we designed the low-cost device for fetal screening. So this is the oldest method of fetal health screening. So that this peanut stethoscope, and the midwife is to listen to the baby's heartbeat through the peanut stethoscope. It was developed more than 1,000 years ago. And actually, when I look at this article long time ago, it was published by BBC, and I was inspired, and then I thought that why can't we do the same thing with the mobile phone, with the let's say the microphone attached to the all the mobile phone has that sound port, and we can just try with this. I tried first device I developed was this peanut stethoscope, peanut cup, and then I just connected this peanut cup with the phone's audio jack, audio port. And then I applied for funding from Bill and Melinda Gates, and then they thought that it was very worth trying, and they gave me some money to start with this project. And then I started further development of this device, and then I have now in this new system that I have done is that this is the piezo sensor, and then I use the 3D printer to print the casing, the outer casing, and I put the piezo sensor inside the casing, and I develop a simple sensor, and that has the audio port. And then I made this kind of harness so that mother doesn't need any measurement. So this measurement will be fixed for any mothers. So we can just, the center point can be placed on the belly button of the mothers, and then it is easy to place on the mother's abdomen surface. So this was the measurement. They're 16 centimeters by 16 centimeters. So it is a square of 16 centimeters length. So this harness was actually developed by my daughter. She used her sewing machine to prepare this harness, and it was easy to prepare and also easy to use by any mothers. And one of the reasons why I made it black, so this black could be placed on the lower abdomen, and the upper could be on the upper abdomen. So the channel 1, 2 would be first upper 2 channels, and the channel 3 and 4 will be the lower one. So it is easy for mothers to understand which one to go down. But later on we remove this black channel. So this was the first device that we developed. So this we use the phone. I don't know whether you looked at this phone jack or not. So it has the stereo jack, has audio jack, has the 4 portion. So first is the left speaker. It gives sound to the left speaker. The second one is the right speaker, and the third one is the common, which is ground, and the fifth one is the microphone. So what we did, we used the force sensor, and the controlling of the force sensors are actually done through this app, and by giving this binary digit. So pin 1 and pin 2, so which is left and right speaker, giving 0, 0 means sensor number 1, and 0, 1, that means left speaker is off, right speaker is on, so that means this is sensor number 2, and the third is that the left is on, right is off, is the third sensor, and both speaker is on is fourth sensor. So by giving this binary combination of this signal to the pin, so microphone will take the signal from the sensor. So microphone will be taking the sensor signal by following these digits. This is the prototype, and then it was able to actually show the you can see the signal of the phonogram on the phone looks like this zigzag, but it is not possible for mothers to understand. So what we did, this is the raw signal that we can see by capturing the signal from the sensors. But if you look in details of the signal, what is inside the signal? For example, you can see there are low frequency variation, and inside this low frequency variation, you can see there are also some high frequency signals. There are some beats. So the lower variation is caused by the maternal breathing, and we can see that the mother's heart sounds are actually coming inside this signal. You can see this is the small boots, is the mother's heart sound. But fetal heart sound, we can see that it is only possible in channel number 3. You can see there the high frequency variation are actually much higher than the other channels. So that means not all channels give the fetal heart signal. Some channels, for example, in this example, you can see the only third channel. So that means if you use the fourth channel, so one of the channels must give the fetal heart sound signal. So we thought that we applied the simple algebra to the simple linear equation solving problem. So if you have 4 unknowns, so unknowns, what are the unknowns? FHS is the fetal heart sound, MHS is the maternal heart sound, MBS is the maternal breathing sound, and the noise. These are the 4, the sources. And the signal that we recorded are the 4 channels. So channel 1, 2, 3, 4. So you can actually make a kind of like matrix by combining these 4 unknowns, X, Y, Z, okay, X, Y, Z, and then D, maybe use the D. So you can solve this unknown variables by just doing the inverse matrix of this coefficient of this channel, of this matrix, and then we can find this unknown sources, which is fetal heart sound, maternal breathing, and noise. So this is very simple linear equation that we try to solve. And now once we apply that linear equation solving, so we can see that from the 4 signals, 4 raw channel signal, we have been able to separate the 3 important sound, which is 4 important components. One is the maternal breathing. We can see the mother's breathing signal. The second one is the mother's heartbeats, heart sound. And the third one is that activity noise. And the fourth one is the fetal heart sound. So we can clearly actually use the mothers can actually listen to the baby's sound from this recording. And this system can also automatically detect that sometimes some channels may not be working fine. So let's say that one of the example here we are showing here that M2 channel is not functioning. So we thought that we can use the correlation matrix to find that which channel is bad channel. So from this correlation we can disable the channel number 2. We can use the other 3 to extract the sources. And so this is one example. You can see the mother's breathing, mother's heartbeat, fetal heart sound is very clear. So now once we have extracted those information, fetal sound, heart sound, maternal heart sound, then we need to prove that whether this is really happening from the fetal sources or the mother's sources, which is mother's heart or fetal heart or not. So how can you validate that one? So we thought that we can simultaneously collect the phonogram with ECG. So we can see the ECG lead, we can see the white color lead ECG and the phonogram sensor attached at the same time. And then we actually went to several hospitals. We went to Al Ain Hospital, Mafraq hospitals. We collected around, we tested on 110 normal pregnant mothers and also 50 complicated cases, fetal ECG and fetal echo. And some of the international hospitals also helped us to collect some data from the pregnant mothers. And then what we did is actually we further improved the fetal heart sound. In the previous heart sound figure, we can see that heart sound was not very clear. So in this figure, you can see the sounds are very much clear. So only peaks are very much clearly seen, and mother's heart sound are also clearly seen. So we use another filter to remove the noise in between the heart sound. And then let me show you some result here for validation. So for the fetal echocardiography and the fetal heart sound that we extracted from the fetal phonogram are actually matched with that Doppler-based aortic blood flow. And when you plotted the the fetal heart rate, the right panel shows the fetal heart rate, the blue color shows the fetal heart rate extracted from fetal ECG. So we can clearly see that the heart rate traces and the variability in the heart rate matches very well from this figure. So if you are interested, you can have a look at this paper. The much more detailed results are actually presented. Now, statistically, we have proven that from the Alpine plot, we can see that the heart rate measured from the fetal ECG and heart rate measured from the fetal phonogram are within the range of this the confidence interval, which is the double of the standard deviation. So which is the mean variation, so mean differences and twice of the standard deviation of the variation. So we can see that the most of the beats are within this confidence interval, which can be accepted as a kind of equivalent heart rate between these two devices, ECG and phonogram. And the correlation coefficient are also very significantly correlated. So in summary, what I'm going to tell you that the potential of the simple sounds transducer to capture fetal heart sound, it is possible. So we have made it possible. But I think the clinical utility testing needs more cases. At this stage, we have only 160 examples, but we need to test it on larger scale. So of course, that is something that we are currently working on. And so something that as I said, that clinical validity on more abnormal cases are needed. and also fetal positions. So this is another thing that that mothers do not realize, that baby's head should be in the downwards, but sometimes in the bridge position can create a lot of complexity. So, but this device has potential to actually recognize the fetal position, so which we have been working on currently, and also, but the overall the clinical applicability in the community setting, the community clinics particularly when they don't have the facilities, the equipment, we haven't tested in developing countries yet, so I think that needs to be tested as well. And for that, actually, we thought that we made a kind of submitted patent. We submitted patent, and that now has been protected by this patent, and then the business plan was actually thought out how to take this device to the developing countries. So because of this, the commercial potential of this device, because of its low cost, it is safe and comfortable wearing, and it can be used for long-term fetal monitoring. A mother's heart rate, breathing pattern could be also monitored at the same time of the fetal positions, fetal movement. Kick chart is also possible by this device. We haven't validated it yet, but we are working on the fetal kick chart by this device. Of course, fetal heart rate and fetal heart rate variability can be also measured by this device. So, so this device, this whole technology was licensed to an Emirates startup company last year. We hope that this device could be commercialized within 2021. That is the expectation, and we are working together with this company to make it happen. And thank you very much for your attendance. Yes, if you have any questions, let me check your question. Yes, one question is about how effective and accurate are the low-cost medical equipment. Yeah, I think this is the very important question, because that we are trying to solve, how accurate. We need more clinical validation, but as you see that our initial result shows that it is error is less than 5% from the traditional fetal heart monitors. So it is error is kind of plus minus 5%, but more validation are needed. Still we're working on, particularly the abnormal cases. We collected only 50 abnormal cases, so we haven't published that result yet. But at the moment, for the normal cases, it is acceptable range. The accuracy is acceptable range. Accuracy in detecting fetal heart rate in acceptable range. Yeah. Any more question? Okay. Okay. Thank you very much.